Dear students, today's topic is electromagnetic wave propagation dash S10. The title of the topic is the plane electromagnetic wave propagation, uh, in which we will be discussing the reflection and refraction at the boundary of the two non-conducting media. There are two cases. One is the normal incidence and the other is the oblique incidence. So we will be discussing the normal incidence. Now let us consider a plane electromagnetic wave traveling along the positive z direction with the E1 and H1 as the incident field vectors traveling in the medium 1. So we are going to tag E1 H1 as a medium 1 with the epsilon 1 and mu 1 permittivity and permeability of the medium 1 properties, which are the electromagnetic properties of the medium 1 respectively, while the E2 and H2 describe the reflected waves traveling in the negative z direction. The field vectors E3 and H3 are described as the transmitted or refracted. Here, as shown in the figure, we can illustrate from here. This is the positive z direction, and this will be the opposite negative z direction. This is the x-axis, this is the y-axis. I, j, and k are the unit vectors. This is the E1 field vector. We are taking the normal incidence as compared to the interface. This is the interface of the two media. This is the medium 1. Here we have mentioned that medium 1. This is the medium 2. The permittivity is epsilon 1. Permeability is the mu 1. K wave vector is k1. Here in medium 2 we have the permittivity epsilon 2, permeability mu 2, and wave vector k2. So E1 vector and H1 vector, these are the field vectors, the electric field and the magnetic field vectors, which are the incident field vectors. What happens that the wave, partially the wave is reflected and some part is refracted or transmitted. The reflected wave is now E2, which is coming back into the same medium, and also H2, but with a 180-degree phase shift. This is a positive y-axis, or the plus j, and this one is a minus j, while the reflected E2 is also having the phase reversion. You can see that it's a 180-degree back to the minus k or the minus z direction. Here we have the transmitted E3 and H3 field vectors. So now let's continue with that. The E3 and H3 represents the transmitted or refracted field vectors in the medium 2, and similarly epsilon 2 and mu 2 are the permittivity and permeability of the medium 2 respectively. Now the interface at z is equal to 0 is coincident with the xy plane. The electric fields are polarized in the x direction, so E is everywhere parallel to the x-axis. So E is everywhere parallel to the x-axis and are given as the E1 is equal to I unit vector E10. Now E10 is actually we initially tagged the E0 only, which is the amplitude, but here we put further the this tag 1 for the incident, tag 2 for the reflected, and the 3 for the refracted or transmitted. And this is the wave equation solution for the E1, which is e to the power j. K1 is a wave vector. We take the magnitude over here, otherwise it would have been in the 3 dimension. K dot r, this is a phase, of that wave, but in this case, since it is along the positive z direction, we take, so k1z minus omega t, this is a time part, so this is a space time dependent E field vector equation. Similarly, E2, since it is reflected back, so we have, so E2, it comes along the same x-axis, but the only change is that the E2 is minus along the z is negative, it is reflected back at 180 degree, so that equation will take the form. E3 is transmitted through along the E3 is along x-axis, and but we have the phase the wave vector. The wave vector is now k2 in the medium 2. So this makes a set of equations A, B, C, and mean of the equation 1. Now in the above equations, we have mentioned that k1 and k2 are the wave vectors in the medium 1 and medium 2 respectively, while E10, E20, and E30 are the amplitudes of these incident, reflected, and refracted wave. The magnetic field vectors are associated with the electric field vector that is also given as the B, which is a space time dependent, epsilon mu square root k cross E naught. This is general B field expressed in terms of the E. So E naught into E is or j k z minus omega t, and or we can B is equal to mu h, so we can put here h is equal to epsilon over mu square root k cross the same remaining the term as mentioned above. Hence the magnetic field vectors in the medium 1 and 2 are expressed as h1 positive, this is a j is a unit vector, this j is a complex the number j under root, which is the complex equation, which is the under root minus 1. So we have clearly obviously mentioned that. So h1 has the positive y-axis, epsilon 1 mu 1 square root E10 e square j k1z minus omega t. So this makes the equation 2a. H2 is, now H2 is reflected, but that is again having a phase shift of the from plus j to minus j. So while it remains in the same medium, so it has the same electromagnetic property, which is epsilon, electric property epsilon 1, and magnetic property mu 1 square root E20 is its reflected amplitude e to the power minus j k1z. Now the minus omega t we take here. In this case, the H2 is that the minus j, we take the minus, actually this is a k1 which is negative, which is reflected back, so minus we take common, and it's a k1z plus omega t. H3 is j normal with the positive all directions respect to the position, positive y-axis, positive z with the wave vector as a k2, and the epsilon 2 mu 2 as the electromagnetic properties as a square root. E30 is the amplitude inside the medium 2, e is for j k2z minus omega t. So these are the three A, B, C, three set of equations of the main equation 2. Now since the normal component of the field vanishes and only tangential components of the electric and magnetic fields are considered as per boundary conditions for the electromagnetic wave propagation. Since the medium 1 and medium 2 are non-conducting, for which we take the conductivity is G1, G2 is equal to 0 for both media. Now at the interface at z is equal to 0, the wave equations 1 and 2 are reduced to the following forms. The Now this we are on the page 4 of the topic S10 in electromagnetic wave propagation. Now E1, then we have the Z parts are 0, then we are left with the E1 is I, E1 0 is minus j omega t. Similarly E2, E3 with only time functions left. So as the boundary conditions, E field vector, as per boundary condition, E field vector in medium 1 and in medium 2 must be continuous. The field vector, the field vector in the medium 1, the field vector sum in the medium 1 is equal to the field vector in the medium 2. So E1 plus E2 is equal to E3. That initially sounds a bit so here we can see that the sum of the E tangential E field vectors in medium 1, because the E2 is reflected back, so E1 plus E2 is equal to E3. So let me illustrate that. Normally it seems odd that incident wave how could be added to the reflected wave, and it should have been E1 is equal to E2 plus E3, which is actually like that, but a tangential component on this side of the medium is equal to the tangential component of the other side of the medium. So let's consider this figure where we have the boundary condition for the tangential component. We have the this is the tangential incident field vector, which is being here at the interface, falling on the interface. We are taking in this case a particular the angle, but we have normally the field vector is parallel to the surface, the plane of the plane. So what we have, this is the E field. Suppose this is the E field. The reflected one is, you can see, it has the opposite direction, so it will be negative in that respect. So what we have the resultant. If this is the one vector, we add these two vectors head to tail, and the resultant is E1t plus E2t, actually, which is E1t minus E2t. We will see in a coming equations that will appear. So resultant is E1t, which is plus E2t is the resultant field vector in the medium 1, and obviously there is a one field vector which is E3. The tangential component is along that surface, parallel to the surface. So putting the we put here the values of the E1, E2 and E3 in this equation 1b from 1a. So what we have, the E10 I plus IE2 is to minus JT plus is equal to minus IE30 is to minus JT. So what we have, E10 plus E20 is equal to E30. So this is the E20 actually contains the inside what is reflected part, since the reflected part that is the net resultant sum over here from the incident we take. So this is equation number 3. Similarly at H, at Z is equal to 0, the magnetic field wave equation is given as H1 plus H2. That should be things as, so actually it is H1 plus H2 is equal to H3. So we move on to the next page, which is page 5. So H1 is equal to J, which is the x positive y axis, J unit vector, epsilon 1 over mu 1 under root E10 dash the E10 is from minus j omega t. What we have, let me turn that off, it's just disturbing the okay. So here we are, the that is the H1 we have. So similarly H2 is, now you can see here the along the there's a change in the phase, minus y axis, minus j is there, rest is the E2 is the E20 is the reflected amplitude, H3 is again the positive y-axis we have got, and epsilon 2 over mu2 E30. So let me show you again once again a quick. A unit vector is the unit vector for the y-axis, while we have again here mention again that the other j which is in the exponent term is the complex j, which is j is equal to square root of -1, also called the j operator in the complex vector algebra. Now putting the above terms of the equation 2a in the equation 3a, we get, putting these values, the term which is we use minus j omega t can be taken common and cancel out from the right hand side and the left hand side, and considering the magnitude terms only, we have the if we take the magnitude, that means the taking the square and taking the under root, then the j we can say that under root of the square root of the j unit vector is 1 unity. So we are left with these terms epsilon 1 mu 1, so we can say here we have that common square root into E1 0 minus E2 0 inside the bracket is equal to epsilon 2 or mu 2 square root E3 0. This is equation number 4. Now let us substitute the E3 0 from equation 3, that is E3 0 is equal to E1 0 plus E2 0 in this equation 4. So, and rearranging the terms, what we will get, that we have put over here on the left hand side E3 0, and just multiply this whole term epsilon 2 over u2 E1 0 epsilon 2 over mu2 into E2 0, and rearranging what we get now, reflected amplitude E2 0 is equal to E1 0, this is the comma actually, it's just E1 0, let me just correct that one. So this is E1 0 into epsilon 1 over mu 1 minus epsilon 2 over mu 2, and epsilon 1 over mu 1 plus epsilon 2 over mu 2, all under the root, each one under the square root. So now putting the E2 0 which is equal to E3 minus E3 0 minus E1 0 from equation 3 equation 4. So what we, and after putting rearranging, what we will get E3 0 is the transmitted amplitude is expressed in terms of the incident amplitude E1 0, as we have in this case as well reflected amplitude in terms of the incident amplitude. Here we get the 2 times epsilon 1 over mu 1 square root divided by epsilon 1 over mu 1 square root plus epsilon 2 over mu 2 square root. So this is equation number 6. So let's move on to the page 7. Now the equation 5 and 6 determine the electric field of reflected and transmitted or refracted in terms of its incident field waves. So if the values of these equations are substituted in equation 1 and 2, so putting back we get the field vectors, actually the field vectors E2 which is equal to I E1 0, the whole term of this epsilon or mu 1 related into e to the power minus j k1, this is the E2 part, minus j into k1z plus omega t. Similarly E3 we get E1 is obviously that remains the same, E3 is equal to I E1 0 the whole term, and e to the power j k2 z minus omega t, which is k2 obviously the wave vector in the medium 2. So these are the E field vectors. Now we would like to, similarly we can find for the magnetic field vectors, the H1 is given by j times the square root of epsilon 1 over mu 1 E1 0 e to the power j k1 z minus omega t. We should have a bracket over here, let me correct that one as well. So j k1 z minus omega t, let's say this is equation number 8a, and then H2 is now we can say this is a unit vector minus j E1 0 epsilon 1 over mu1, the whole term is to a minus this is the term which is already carried by the H2, so minus j k1z plus the k1z plus omega t. Similarly, so we have H1 H2, the H3 is now 2j E10 putting the respective whole term e to power j k2z minus omega t. So these are now the actual field vectors. Now let us express these field vectors, rather these equations of the incident to the and the ratio of the amplitudes in terms of the, that is, we get the reflected in terms of the incident, the reflected and refracted amplitude in terms of the incident. So let's move on to see the how this propagation of the electromagnetic waves are related with the refractive index, how we transform them, and what happens, how the refractive index if is affected. The refractive index is due to the electromagnetic properties of the medium. So let's the n is the represented the refractive index representing the refractive index. The refractive index of a medium is defined as that it is the ratio between the velocity or the speed of the light in vacuum to the speed of the wave in the medium through which it travels. Now it is denoted by n, so n is equal to c divided by u. C is the speed of light in vacuum and u is the speed of the wave inside the medium. In vacuum, where c is the speed of light obviously, and u is the phase velocity or the velocity in the medium. So n is equal to speed of light in vacuum divided by speed of the wave in the medium. For optically transparent medium, mu1 is equal to mu2 is equal to mu naught. So for free space vacuum or vacuum, we have epsilon 1 is equal to epsilon naught epsilon r1, while the epsilon 2 for free space obviously we put the epsilon r 1 is equal to epsilon r1, relative permittivity is equal to 1, but here, so what we will be having, the epsilon 2 is equal to epsilon naught epsilon r2 epsilon 3 epsilon naught r3. So this term will be equal to epsilon 1 will be equal to epsilon naught, while the other term will remain there. And okay, so what we have, the 2 is we will see that, but a medium similarly in the medium 1 we will be using the relative permittivity to be equal to epsilon naught. So the speed, the phase velocity v is 1 over 1 divided by epsilon into mu square root. So since mu is equal to mu naught, we have epsilon mu naught, or c is equal to if we put further epsilon for vacuum, epsilon is also epsilon naught, so c is equal to 1 over epsilon naught mu naught square root, which is speed of light. So in vacuum, putting the values of the c and u in the last equation of the refractive index, which we put over here, this is the speed of light which is in vacuum, 1 over epsilon square root of epsilon naught mu naught and 1 over epsilon mu naught. Rearranging and cancelling the terms, what we get, we are left with the now refractive index is nothing but the ratio of the two permittivities. One is the for the free space epsilon naught. In this case, we have taken the first medium, the medium 1 to be the free space vacuum. Otherwise, if the medium would have been any other denser medium, there we would have been putting the relevant permittivity over here as well. So epsilon to epsilon naught, this is a general term here representing. Hence for the medium 1, let the refractive index is n1, and for the medium 2 is n2. So n1 is equal to epsilon 1 over epsilon naught, and 2 is equal to epsilon 2 over epsilon naught. Now let us now divide the equation 7a by 7c, which gives the ratio of the reflected to the incident amplitudes and putting n1 and n2 values, what we get, epsilon 2 or epsilon 20 to epsilon 10, it is the whole term. And now we put the epsilon 1 over epsilon mu naught, which is n1 minus n2, n1 plus n2. So we saw that the reflected to incident wave is now expressed in terms of their refractive indices. So these electromagnetic properties have the effect on this the wave, incoming wave. So we have the n1 minus n2 divided by n1 plus n2. So equation 9 gives the ratio of the reflected to incident wave. We move to the last page, which is page 10. Now to get the ratio of the transmitted to incident wave, let us now divide 7b, equation 7b by 7c. What we get, E30 divided by E10. So that is equal to the whole related terms we put over here, rearranging the things and simplifying, and putting now the epsilon 1 over mu naught, which is n1, which is this term will give you 2n1 divided by n1 plus n2, is equation number 10, where n1 and n2 are already defined as the refractive indices of the two media, medium 1 and medium 2. So for optically transparent media 1 and 2, the equation 9 and 10 are known as the Fresnel equation for normal incidence of the plane electromagnetic waves. So students, we reach to the end of the this topic. Inshallah, we will meet again in another topic next time. Thank you.